Well, this is lecture 30 of basic calculus 1. Recall that we had introduced the integral through a particular type of area. So, suppose y equal to f of x is a curve and we wanted to find out the integral from a to b f of x dx. So, we take the area between x axis, the curve and the lines x equal to a and x equal to b. This area was defined as the integral a to b f of x dx, definite integral. So, now we turn it around, we take different kinds of areas, another one particular type of area which is not of this type, but it is bounded between two curves and they say some lines. Then how to compute those area? Now that we have fundamental theorem of calculus, we know how to integrate some of the functions. Then we use those techniques and express these new types of area as some definite integrals and evaluate the definite integrals for computing the area. That is what we will be doing. So, we will be talking about area between curves. Okay. So, let us take first the case of non-intersecting curves. Suppose we have two functions, say y equal to f of x, which is in blue here, and y equal to g of x, which is in yellow here, and we want to compute the area between these two curves, and on the left bounded by the line x equal to a and on the right bounded by the line x equal to b. So, this is the area which is painted blue here. That area of that region, how to compute that? That is our problem now. And in all those things we have assumed that this for any x inside this interval a to b, f of x is greater than or equal to g of x, it is to the top, right. So, we start with suppose f x and g x are two functions satisfying the condition that f x is greater than or equal to g x. Then we take R 1 to be the region bounded by curve y equal to f x and the x axis and x equal to a, x equal to b. So, that means it is the area. Suppose you take the R 1 is the region bounded by curve y equal to f x. So, this area and this area, these two regions union of that, and R 2 be the region bounded by the curve y equal to g x, x axis, and again y equal to g x. So, it will be this area union of this area. Now, how to get the area of the region bounded by these two curves and the on the left equal to x equal to a and the right x equal to b. So, that you can see it is the signed areas that first you take for f of x, then subtract it the g of x and you would get that area, right. So, it might not be always in this form, you can think of some other type, say f of x and g of x both lie on the above the x axis, you have x equal to a, x equal to b. Then you can see that area of this region will be equal to area of f x bounded by x axis. So, the whole thing minus area bounded by g x and the x axis, this one. So, that is easier to see in the other picture. Sometimes it may happen that both of them are downside, that is below the x axis. So, one can be f, another is g. So, here f is here and g is here. Then again to get the area, you take this area minus the whole area, it is the signed area we are taking. So, that will again give us this region of this area of this region. So, here if it is in the picture, it is given that one of them is lying really below, but it is also going to the below x axis. Other one also has some parts on the above x axis and some parts below x axis, but still you can get the area by taking f of x minus g of x, right. So, particularly this area, it is f of x and then here it is g of x. When you take the signed area minus, it will be plus of this, right. And on the other side you have f of x bounded by this one and minus of the signed area you are taking, again you get back this area. So, they are plus. which is same thing as fx minus gx. Okay. So, that is how we get integral a to b f of x minus integral a to b g of x, which are these two areas. That would give us integral a to b fx minus gx. That will be the area painted blue here. So, we will be using this in many examples and see how one curve is lying above the other on the top of that. So, you get one of them f of x is greater than or equal to g of x for each x in a b. That condition is required, and of course, integrability conditions should be satisfied. We usually assume that f of x and g of x are continuous functions. So, you may say continuous here itself, so that these integrals are well defined. Okay, let us apply this. All that we remember, if f of x is greater than or equal to g of x for every x in a to b, and you can integrate them, then the area bounded by those two and the lines x equal to b is integral a to b f x minus g x dx. Okay. So, let us see other cases. In fact, if there are this is non-intersecting curves, right, f x and g x never intersect, but suppose they intersect, then what can we do? Suppose something like here is f of x and it is g of x, something like this. So, then what we do? We break that into two parts wherever the intersection point is. Here the first one is f is greater than or equal to g, next one is g is greater than or equal to f. So, you may say it is a to c and c to b. So, the area between those two curves can again be got, but one is integral a to c f x minus g x plus integral c to b g x minus f x, fine. So, once they intersect, this condition will be satisfied, that in one of the intervals f x is greater than or equal to g x, in the other f x will be less than or equal to g x. Okay. Then we can find out the areas. So, that is what we will be doing. Let us try one example. Say, find the area of the region enclosed by the line y equal to minus x. So, y equal to minus x is this line in yellow, and the parabola y equal to 2 minus x square, which is the blue one, and nothing else, no line on the left x equal to a or x equal to b. So, that means it is assumed that these two curves intersect at least 2 points. So, that between those 2 points you can find out, and it so happens one is a line, another is a parabola. So, if they intersect exactly at 2 points. So, you get one point here x equal to minus 1, another point x equal to 2, but let us find them. It is picture may be misleading sometimes, we do not know whether it is plotted correctly or not. So, let us find them out by solving the equations. So, to find the intersection points y equal to minus x and y equal to 2 minus x square, we eliminate say y. So, we say minus x equal to 2 minus x square. So, that gives x square minus x minus 2 equal to 0, which is x plus 1 into x minus 2 equal to 0. Just multiply x square minus 2x plus x, this gives minus x, and minus 2 equal to 0. So, we get the intersection points as x equal to minus 1 and 2. These are the two intersection points as the plot says, and we need their values. If you want the values at those points, then we find out from any of them. So, y equal to minus x gives y of minus 1 is 1 and y of 2 equal to minus 2. So, we have the points now, points of intersection as minus 1 comma 1 here, and then 2 comma minus 2 it is here. Now, you want to find the area, which is area of the region, which is painted blue here. So, we just go for the formula, but before that we should see whether one of the curves is lying always greater than or equal to the other curve or not. Okay. It is from minus 1 to 2, the plot also says that, but we should verify, like from when x varies from minus 1 to 2, we see that minus x less than or equal to 2 minus x square. or since it is really from x plus 1 into x minus 2 equal to 0, this x plus 1 into x minus 2, that is the expression here. So, you can say 0 less than or equal to 2 plus x minus x square. So, once that happens, that means our curve f of x, which is the parabola y equal to 2 minus x square, is greater than or equal to the curve which is the straight line y equal to minus x. So, this condition is satisfied. Therefore, the required area will be integral from minus 1 to 2, and 2 minus x square is bigger than minus x. So, it is 2 minus x square minus of minus x, f of x minus g of x, and its integral. So, when you get the integral, it is 2 minus x square plus x. So, 2 it is giving 2x integration, and minus x square gives minus x cubed by 3, and x gives x square by 2. So, this is to be evaluated at 2, evaluated at minus 1, and then subtracted out, fine. So, that turns out to be, when simplified, becomes 9 by 2. This is how we will be computing areas. But it might so happen sometimes that you have to look it from the y axis side instead of x axis, which may become easier sometimes. We will see in one of the problems. Okay. So, here is another problem. We want to find the area of the region in the first octant. So, these curves might intersect somewhere else, we are not worried, only in the first octant, that region we want, which is bounded by the lines y equal to 0, that is x axis, y equal to x minus 2, that is this yellow line, and the parabola x equal to y square, which is the blue curve. So, that is, it is the area, this is the area, right, this is the region. So, you want to find the area of this region. Now, you see that this area is not just bounded by two lines, vertical lines, and then two curves as our earlier thing, but there is something else is happening, fine, because on the below you have another which is x equal the x axis. So, that means we break at this point 2 and we pose this area as sum of two areas. One is this A, another is B, which is painted brown, and then B, which is blue. So, here in the for the region A, we have the curve y equal to root x, which is your x equal to y square in the first octant. So, y equal to root x on the top and y equal to 0 on the bottom. And for B, we have y equal to root x on the top, and below you have y equal to x minus 2. So, those two integrals have to be obtained separately and then added together. That is how we will be getting the area of the region required. So, now we have the upper curve as root x and it has two lower curves with breakpoint at x equal to 2, that is what we mentioned. So, when x belongs to, that is x now belongs to 0 to 4, you can get this 4 because it is the curve, it is the point of intersection where this blue and the yellow meet. That has to be found out, of course, algebraically, and that is easy. You have y square equal to x and another is y equal to x minus 2. So, if you solve them, you would get that the point is 4, 2. So, that is how we have obtained, and correspondingly we have x equal to 0 to 4, x varies from 0 to 4, and we have breakpoint at 2, that is two different regions are coming where upper curve and lower curves are different now. Okay. So, when x varies from 0 to 2, the lower curve is y equal to 0, upper curve is y equal to root x. That is what we discussed. Okay. And on the other interval, when x varies from 2 to 4, the lower curve is the line y equal to x minus 2, that yellow one, and upper one is again y equal to root x, fine. So, divide the region and then required area will be equal to sum of two integrals. It is 0 to 2 into root x is lying to the upper part of x axis, which is y is equal to 0, So, that will correspond to the integral square root of x minus 0, and from 2 to 4 it will correspond to the integral root x minus 2. So, this step is crucial. After that it is usual computation with the integrals. So, now when you take x to the power half, that gives x to the power 3 by 2 divided by 3 by 2, which is 2 by 3, and that is to be evaluated at 0 and 2. Similarly, the other one, it is root x, so that gives 2 by 3 x to the power 3 by 2, and it is x minus 2. So, it is x minus 2 square by 2, and whole expression is to be evaluated at 4 and 2, and then subtracted. So, we do that and we get the answer as 10 by 3. Fine, but there is another way of looking at it. Just look at the picture. If you look at the region from the y axis, view it from y axis from the other side, then you can see you have the curve x equal to a function of y, which is the yellow one. This is x as a function of y, and then you have the parabola as x as a function of y again, right. So, let us write g of y. So, you see that this is lying from this side. If you look from the y axis side, yellow one is on the top of the blue one. So, the whole region can be thought of as integrating with respect to y, and that will be integral g y minus f y, right. So, that is what we do in the alternative way. We see that the upper curve is line x equal to y plus 2, which is y equal to x minus 2. Same thing, we write x as a function of y now, and the lower curve is x equal to y square, where y varies from 0 to 2, right. That is what you see from the picture. So, y varies from 0 to 2 is the point, intersection point is 4 2. So, we write the integral correspondingly, one integral only, which is 0 to 2, y plus 2 in the top, y square in the bottom. So, y plus 2 minus y square dy. So, that directly if you integrate, y gives y square by 2, 2 gives 2y, minus y square gives y cubed by 3, to be evaluated at 0 and 2 and subtracted. So, that again simplifies to the same answer, 10 divided by 3. So, you see in one approach through the x axis, it is really, we could break it down to two integrals, sum of two integrals, whereas looking at it from y axis, we could write just as one integral. So, sometimes one may be easier, the other may be difficult. We have to really see what is the picture of the region and then decide which way to move. Okay. Let us take another problem. Here we want to find the area of the region bounded by the x axis and the curve y equal to x times square root of 4 minus x square. So, it is asking just to find the region bounded by these two curves. So, one is a line x axis and the other one is x into square root of 4 minus x square. So, which means implicitly it is assuming that this curve y equal to x into 4 minus x square intersects the x axis at least at 2 points. So, let us find out when does it intersect the x axis first. So, to get the intersection, we have y equal to x into square root of 4 minus x square and y equal to 0. These are the two curves. So, eliminating y, we get x square root of 4 minus x square equal to 0. That gives us now not 2, but 3 points. Hence, the area or the region bounded by this curve and the x axis now has two pieces, right, one from minus 2 to 0, another from 0 to 2. So, each of these pieces have to be computed, their areas computed and then added together, fine. So, the required area will be A equal to minus 2 from 0, that is the intersection point, minus 2 from 0, and it is top is y equal to 0, bottom is that curve. So, it is 0 minus x into square root of 4 minus x square dx. Of course, if you go back to the definition, it will be simply modulus of that, modulus of x square root of 4 minus x square, and since x remains negative, it will become minus. That way also it is giving to the same expression. And then we add the other area, which is x varies from 0 to 2, where the upper curve is x into square root of 4 minus x square, and the lower one is y equal to 0. So, that gives x into square root of 4 minus x square minus 0. Now, it is a matter to evaluate the integral. How to evaluate? We have anyway to evaluate x square root of 4 minus x square dx, this integral. Now, we find here that x dx is really half of d of x square, or even we can take 4 minus x square directly. There is a constant that will become 0 and one negative sign will be added. So, we substitute u equal to 4 minus x square, fine. So, once you take u equal to 4 minus x square, its differential du is minus 2x dx, 4 gives differentiation as 0. Now, we have to talk about the limits. So, minus 2 to 0, x equal to minus 2, u equal to 0, right, 4 minus x square. Also at minus 2 it is equal to 0. So, that is what we say when x is plus or minus 2, u equal to 0. And when x equal to 0, substituting there, you get u equal to 4. Okay. So, we can rewrite the integrals in terms of the variable u now. The limits now minus 2 to 0 become 0 to 4, and this is, it is x square root of 4 minus x square. So, that is x square root of 4 minus x square dx. So, this differential will be written as half square root of u du. Let us see whether that is correct. When you come to u equal to 4 minus x square, you get du equal to minus 2x dx. So, this is minus 2x dx, and square root u equal to square root of 4 minus x square. So, your 2 cancels and you get that minus sign here also, right, minus x. So, first integral is all right, it is minus x square root of 4 minus x square, this is half square root of u du, and the other one is x into square root of 4 minus x square. So, that gives minus half. So, this is really for the minus sign, you get minus half square root of u du. Then once you integrate, it is u to the power half. So, its integral is u to the power 3 by 2 divided by 3 by 2, it is 2 by 3 and then minus half, right. So, that gives 2 by 3 into half into u to the power 3 by 2, fine. So, these 2 cancels, you have 1 by 3 u to the power 3 by 2 evaluated at 0 to 4, and the other one is 4 to 0 minus half. So, again that becomes 0 to 4. So, that is same thing as telling this sum is equal to 2 times integral 0 to 4 half root u du, which is equal to integral 0 to 4 root u du, and that is what we wrote here 0 to 4 root u du, which gives you 2 by 3 u to the power 3 by 2 evaluated at 4 and 0 and subtracted. So, that gives again 16 by 3. So, this is how we are going to evaluate the areas by breaking it whenever we need, but the main thing is we have to express in terms of two functions, y equal to f x, y equal to g x, and the region should be bounded by those two curves. That is important. That is how we get this way of breaking the region.